Hey everyone, welcome to part 4 of Motion Along a Straight Line. I'm JLou from toysandphysics.com, and on this video I want to share with you the analysis of a graphic and how from something that initially may seem incomplete and intimidating, we can actually describe more things than are visible at first sight. I invite you to visit toysandphysics.com for more information so that you can do a deeper analysis of these concepts. Also, this fourth part builds upon the content of the first 3 videos. And if you haven't watched those, I recommend you to do it, since we'll be using the concepts developed there to continue our journey here. Here's a position versus time plot of an elevator cab that is initially stationary. The cab then moves upward, which is the positive direction of the position axis, and after a while it stops. The instruction is, with the information given in the position time graphic, plot velocity versus time graphic. Like I said, you can visit the page of Motion Along a Straight Line right now at toysandphysics.com to see the result. But if you want to know how to approach this and understand how to make the analysis, then follow along. By the way, something interesting about this problem is that it really makes us think, since most of us are used to see a problem, collect the givens, list the unknowns, and then reach out to a cheat sheet with formulas and equations to solve the problem. However, it's not the case here, since the problem statement is the graphic itself. So we are forced to watch the graphic and start connecting the dots from there. Just to help you a little bit, I added a short animation at the left-hand side for you to have a better picture of the situation. So like I said, this may seem an incomplete problem statement since you can think we are missing data, but it's not true. Let's start by looking at the graph and see what we have here. The first thing I notice is that the blue line describes the movement of the elevator cab. That is, the blue line describes the position of the elevator cab with respect to time. Also, there are 4 points of interest along the curve that can help us to determine information that we need to plot the velocity versus time curve. These points in red are labeled with A, B, C, and D lowercase letters, and we can use them to complete our analysis. Let's start by analyzing point A. While we don't have any clear information on this, it is observable that from 0 to 1 seconds, the position of the elevator cab remains at 0. From this observation, we can say that the curve of velocity versus time would start with a horizontal and straight line from 0 to 1 seconds at 0 value of velocity. By the way, we can conclude this not only because of an observation, but on a previous video, we already learned that the slope of the curve on a position versus time graph is the value of b on the velocity versus time graph. Since the slope of the curve of position versus time is 0 from 0 to 1 seconds, it must be true that the value of velocity on the velocity versus time graph is also 0. So this is a type of analysis we are going to do all over the curve of position versus time to predict how the curve of velocity versus time would look like. Moving on, it is when the clock is at 1 second that something starts to happen with position until point B. From the graph, we can tell that point B is reached when the clock shows 3 seconds. Again, we don't know much about the curve from 1 to 3 seconds, but we can definitely tell there is not only a slope there, but also an increasing one. So the value of b must be increasing from 0 to something else during these 2 seconds. That is as much as we can tell right now of what happens with the velocity curve from 1 to 3 seconds. So for now, we'll leave it there. Let's continue to watch the position curve and see what else we can tell about it. If you notice, once the position curve reaches point B, it describes a straight line until point C. All straight lines have a constant slope until they reach a breaking point, that is, a point where they are no longer straight. If this is a straight line from B to C, then its slope is the same along that portion of the movement. And therefore, the value of B on the velocity versus time curve must be, anybody? Constant. That's right. The value of b on the velocity versus time graph must be constant from b to c. This means that we'll draw another horizontal line from 3 to 8 seconds on the b versus t graph. But we're not done yet, because we have some additional data that can help us determine the value of b from 3 to 8 seconds. If you notice, there are 2 pieces of additional data here that say that the position of the elevator cab is 4 when the clock is at 3 seconds. And 5 seconds later, when the clock is at 8 seconds, the position of the elevator is 24 meters. From this information, we can calculate the velocity of the elevator cab during those 5 seconds. We will do this using the average velocity equation. Now, since the velocity of the entire portion from B to C is constant, then we can say the value we calculate is for B, C, and the time in between. The average velocity equation says that V equals delta x over delta t. Delta x is 24 minus 4, and delta t is 8 minus 3. Whatever is the result of that is the value of v in the velocity versus time graph from B to C. Okay, so far we have predicted how the velocity curve will look like until point C, but we have to reach point D as well. From C to D, it is observable that the elevator cab slows down. You can tell this for the animation and also because the position curve describes a smaller displacement over a longer period of time. Again, we don't know much information here about the position curve, but just like we did from A to B, we can anticipate a decrease in the value of B from what we previously calculated down to 0. Why 0? Because the position curve seems horizontal again, starting from 9 seconds and on, where point D is. This means no slope. Also, we know the elevator eventually stops, so by definition, if there is no displacement, the velocity must be 0. To put it clear, once the clock shows 9 seconds, the elevator has stopped, and therefore velocity must be 0 from that point on. So, are you ready for the reveal of the velocity curve? Make sure you have your own version ready so you can see if you got something similar to what I'll show you. If you do, congrats. This was a bit challenging because, like I said at the beginning, the problem forces us to leave our comfort zone and see things in a way not everyone is used to. If not, don't worry. This is a muscle that you'll continue to exercise, so keep working. So here it is. Like we predicted, the velocity curve starts with a horizontal line from 0 to 1 at 0 value for B. Now, from 1 to 3 seconds, we have an increasing value of the velocity since we knew there was a change in the ratio of displacement to time. Then, the curve reaches a constant from B to C, and we have a horizontal line at 4 meters per second, which is a result of the calculation I mentioned before. Last but not least, we have a slowing down of the elevator cab, and thus the velocity goes down to 0 from the 4 meters per second value we still had at point C. The value of B continues to be 0 from there. On the left hand side of the page, I put a brief explanation to this in case you want to check it. Again, all of this is available at toysandphysics.com, and then go to the page of motion along a straight line. I'll be sure to leave a link in the description below for your reference. Now, with this, we have completed what we were asked to do, to plot the velocity versus time curve. However, we can go one step further and plot the curve of acceleration versus time. To do this, we have to do the same analysis we did for the position curve. We'll use the same points and sections we used for the velocity, and a key piece of information that says that the slope of the velocity versus time graph is the value of acceleration on the acceleration versus time graph. If you kind of think you're having a deja vu here, you're not far from the truth, because just like B is the value of the slope of the position time curve, A is the value of the slope of the velocity time curve. So from the velocity curve, we can tell there is no slope from 0 to 1 second. So that means acceleration must be 0 as well for that period of time. Then from 1 to 3 seconds, the velocity curve has a slope, which means that velocity increased as a result of an acceleration. Thus, we can calculate the value of the slope of the curve from 1 to 3 seconds to determine the value of acceleration. Also, the curve of velocity is a straight line on this section, so the slope is a constant value, and thus we can predict a straight and horizontal line for the curve of acceleration at the value we calculated from 1 to 3 seconds. At 3 seconds and until 8, the curve of velocity is a straight horizontal line with no slope. This is because the velocity is constant for that period of time. Thus, acceleration must be 0 for that period of time. Then from 8 to 9 seconds, the velocity curve has a negative slope, which means that velocity goes down as a result of a negative acceleration. To know the value of this negative acceleration, we can use delta V over delta T, which by the way is the definition of average acceleration. Something we'll see later, but essentially we are calculating the slope of that portion of the velocity curve. How do I know acceleration is negative? 3 things. 1. The slope of this portion of the curve is negative. 2. The only way to explain a decrease in velocity is with an increasing acceleration in the opposite direction of velocity. Although velocity is decreasing at this point, it still has positive value, so therefore acceleration must be negative. 3. I've solved the problem before recording the video, so I know for a fact this number is negative. Come on, I have to come prepared to these video sessions. So again, the value of the acceleration must be negative, and we can anticipate a constant value that is a horizontal line, since this section of the velocity curve is also a straight line. And finally, at 9 seconds, the velocity goes to 0, and therefore acceleration must do the same. So once again, if you were following along, make sure you have your version ready for the reveal. Pause the video if you need to make the final adjustments. And 3, 2, 1. Here it is. This is how the curve of acceleration looks like. Again, if you got it, congrats. Keep up the good work. And if you didn't, I would say the same. Keep working. You'll get there. The trick with this type of problems, and eventually all problems in physics, is to think about what is happening and start connecting the pieces of information we have to build the solution. So don't give up. This is a muscle, and thus it can grow and become stronger. That is all I have for this video. Again, if you have comments, please let me know in the section down below, and we'll catch up on the next one. Bye for now. Thanks for watching. I hope you enjoyed that video and help you better understand how to analyze a position versus time graphic, and from there make some educated conclusions. If you want to know when a new video is uploaded to the channel, I invite you to subscribe to not miss any new content I upload. If you enjoy the video, please give it a thumbs up to help me support the channel and thus continue creating these videos.